Okay, question 3. Question 3 appears to be in two parts, where we have the first is a Bernoulli's principle question, and the second looks to be some kind of kinetic energy, potential energy, conservation of energy type vibe. So let's deal with 3A first. These are two separate and discrete questions. At least the first one's worth 12 marks this time. So let's give it a go. We're going to draw a diagram, state relevant formulae. Okay, so fluid of a given density flows through a pipe increasing in diameter from 120 to 200. The pipe drops 40 meters at the second point. Okay, that's enough to get started. So the way I draw these diagrams, if I show my small entry point, show the drop, and I show a large exit point there. It's probably worth actually exaggerating that a little bit, to be honest with you. There we go. That'll do us. So we've got at this end what they call the head. It's on the flat, so the H1. So this, I'll refer to this entire end as 1 and this entire end as 2. So H1, the head at 1 is 0. The head at this end, so H2, it tells us there's a 40 meter drop. So 40 meters. Okay, there's a fluid of density. Now, density is just a constant throughout the entire equation. And the pipe increases in diameter from 120 mil, so diameter 1 is 0.12 meters. Oops. Remember, always try and convert on the fly and write it indirectly. So that'll be 0.2 meters, because it'll just save making silly mistakes later on down the line. The pipe drops 40 meters. It has an applied pressure of 1.2 bar at the entry point. Now a bar is times 10 to the 5. So the pressure 1 is going to be 1.2 times 10 to the 5. It gives us a volumetric flow rate. Okay. Of 90 litres per second. So that's going to be using, I should expect, the continuity equation. We'll come on to that. Calculate the applied pressure at the second point. So we're interested, the ultimate goal of this is to find P2. Okay. So we've drawn a diagram, we've stated our variables, let's state relevant formulae. So the continuity equation, which is going to be Q, I'm going to rephrase that to Q, V dot something I used in a previous life. So Q, 90 litres per second, Q is equal to A1 V1, which is also equal to A2 V2. So continuity equation all that means, that is a posh way of saying that unless there's a hole in the pipe and water's dripping out somewhere, the amount of fluid we put in at this end also comes out this end. Water or fluid is not created and it is not lost. And if we put it in at a certain rate, squeeze the pipe so that it's smaller at one end, then the water will speed up in order to maintain the same volumetric flow rate. Okay, the other important formula is the Bernoulli equation. So Bernoulli's, which is a really nice one because it's effectively conservation of energy. Remember that potential energy is mass times gravity times height. Kinetic energy equals half mv squared. Do you see what they've done? I've just spotted the link. Fluid energy, potential and kinetic energy, it is related after all. Okay, so mgh, just keep those in mind. Bernoulli's equation says that pressure 1 plus rho gh plus a half rho density v1 squared, that's that one, is equal to the same on the other side, p2 plus rho gh2 plus a half rho v2 squared. In other words, the total sum of the pressure, the potential energy due to the head, and the kinetic energy due to the movement of the water is maintained. We're not somehow, by means of a pipe, creating or destroying energy. If we could do that, then I'm sure Stephen Hawking will want to know about it. So I'll just move these. Will I do that? No, I won't. I'll leave them where they are. Okay, let us put in some values into our two equations and move on to find our ultimate goal of finding P2. Okay, so I'm going to start by plugging some numbers into the Bernoulli equation. I suspect, well, more than suspect, I know that I won't have all the information that I need, but we can at least make a little start with it. Right, so P1 is 1.2 something's going wrong with my graphics tablet. Let's try again. Oh dear. Problem solved. So P1 is 1.2 times 10 to the 5. That's our pressure. Plus rho gh1. Well, h1 is 0, so 960 times 9.81 times 0 is going to be 0, so I'll leave that. Then I've got half rho v1 squared, half times rho, which is 960, times v, what, velocity, input velocity. Can't do that. I guess I don't think I've been given it. I've got rho there, I've got diameters, pipe drops, got head. Right, so that is an issue. So we'll just put that in v2 squared. Then on this side we've got p2, that's the thing we want to find, plus 960 rho, the density of the fluid, times 9.81, gravity on Earth, times h2, which is the head, which is 40, plus a half times 960 times v2 squared, and we're not given v2 either, the exit velocity. So we need to find those two before we can move on. So for this we're going to use the continuity equation. Now, just worth bearing in mind this little bit here, 90 litres per second, 1,000 litres. 90 litres is actually divided by 1,000, that's going to come out as 0.09. Meters cubed per second. So we can plug that into this thing, hopefully, to find out A1 and V1. So let us do that now. So we know that if we just take the phrase Q equals A1 V1 and deal with that bit first, then we'll have 0.09 is equal to A1. Now we're not given the diameter, the area, but we're given diameter, so that'll be pi times 0.06 squared times V1, which are unknown. Divide both sides by this value, move it across. I like that trick. And we will calculate that to be equal to 7.96 meters per second. That's the input velocity here. Output velocity, well, we can do a similar kind of thing, can't we? I'm just going to butcher this equation. If I use this element of the phrase here, A2V2, then it will be, instead of 0.06, it will be 0.1. And it will be 0.1, of course, because that's pi times r squared. That's the area of this bit here. And diameter is 0.2, so the radius is 0.1. So 0.09 divided by this is going to equal, this thing is going to equal 0.09 divided by pi times 0.1 squared. Stick it in your calculator all in one to prevent errors. That's going to equal 2.86. Quick logic check. That if we open up the aperture from the input, then it will have a drop in speed, which it does. So that's sensible. And they look like sensible values as well as not going through it like Mach 4 or whatever, which is good. Okay, so that's how we use the continuity equation to deal with missing values. So I'm just going to get rid of that bit for now. And we will continue on with this. In fact, for ease, I'm going to save rewriting it. You have to watch me rewrite it. I'm going to copy this thing here. And I'm going to insert the values of V1 and V2 in here. So that will be 7.96 and that will be 2.86. And now what we will do is we will crunch these numbers. I'm just going to pause the video and do that because it'll be quite laborious for me to do it whilst recording. Okay. So we've crunched that and we end up with 150,413.57 is equal to P2. We still don't know that. But when you resolve this bit, that comes out as 380,713. So I'm going to get P2 on its own, I'm going to take that from both sides, and we'll end up with P2 equaling 230,299.44, which is equal to 2.303 times 10 to the 5. If you remember, times 10 to the 5 means bar, so we can say 2.3 bar is our final pressure. Excellent. That's Bernoulli's and continuity equation. Generally, those two equations are used in tandem. I recommend plugging in all your data into the Bernoulli's equation, working out what you're actually missing, typically velocities, and then using continuity equation to deal with it from there on. Okay, on to question 3b. And strap yourself in for this one. There's more to this than meets the eye. So, first off, we know it's something to do with a hammer falling down over a distance on Earth. So, it's a conservation of energy question. And it's worth just stating, first of all, that potential energy, mass times gravity times height, and kinetic energy, sort of movement energy, is equal to half mv squared. And for a given object, energy is conserved in any interaction. So if you drop a ball off a tennis, off a, table tennis table, then that ball will have a mass. It'll have mgh at the top. But by the time it hits the deck, half mv squared, you can work out the actual speed that the thing was going when it hits the floor by setting mgh equal to half mv squared. And in essence, what we're going to do is, instead of having a ball dropping off a tennis table, we've got a hammer swinging from a height. It's my hammer. Swinging from a height of, from 4 meters, seemingly, and we'll be able to work out the speed that it hits the deck. Okay, that's part of it. The other part is why this is a little bit more complicated than you first might expect. And it's this rebound thing that got me thinking about it. There's an aspect of momentum in this question. Now, in classic momentum, in mechanics, momentum is equal to mass times velocity. And you have a thing called the conservation of momentum. Typically, you'll have, think of a tiny little Mini hitting an enormous truck. If these two collide whilst going at the same speed, then the momentum of the truck will mean that in this idealized situation, the two would stick together as one and move in this direction. I mean, in reality, this would just vaporize, but in classic mechanics, they would stick together and move together as one. If the Mini was to impact the truck and the truck would have to move backwards, then this Mini would have to be going at some pace. It would have to be going extremely, extremely, extremely fast to overcome the momentum of the slow-moving truck. And if the speed of the Mini was high enough, and somehow it was made out of some kind of magic material where it didn't vaporize, then they would stick together and move forward as one. And that's the principle of conservation of momentum. That's what we're going to end up with here. So it's probably worth you just bear with me for the explanation of the question. Watch it through and then just attempt the question yourself again and again. Change the numbers out. Get used to the process. Okay, let's go for it. So we're going to, first off, we've actually got quite a nice diagram here that we can lift, to be quite honest with you. Thank goodness they didn't have us draw this ourselves. That will be a nightmare trying to interpret the words of this. So I will copy that out here, and I've already stated my equations that are relevant here. I neglected to put in conservation of momentum, mass times velocity 1, mass times velocity 2. Similar to continuity equation, actually. A1v1 equals m2v2. You might say it's quite similar. In retrospect, I see why they've grouped this with the fluid question. So let's give it a go. So we're going to start off, work out the conservation of energy for the hammer, and we should be able to work out the speed that it hits. So mgh is equal to half mv squared. In other words, all of the potential energy will be converted to kinetic energy, and this is for the case in the hammer. We're just worrying about that hammer at the moment. It's got a mass of 100 kilos. It's on Earth, so gravity is 9.81. It's coming down from a height of 4 meters. That all gets converted into velocity. So the mass remains at 100, and the velocity is the unknown quantity. So I'm going to crunch that in a calculator, and I will have 3924 is equal to 50v squared. Divide both sides by 50. and then square root that to find V. And we find out that velocity is equal to 8.85 meters per second. Now that's the speed of the hammer when it actually impacts in this first case here. We're trying to calculate the loss of kinetic energy overall. And so really what we need to do is find out how much that thing slows down by when it hits the post. How much does it actually slow down by? And for this we're going to need this momentum. So bear with me while I do this. So we're going to say that if this is case 1 and this is case 2, then conservation of momentum is going to tell us that M1 V1 is equal to M2 V2. So the mass of the hammer in the first place was 100 and it was travelling at a velocity of 8.85 meters per second. And this is where it takes a little bit of concentration. Like the Mini and the truck, how they fictionally stick together as they move along, the same has happened here. The hammer has impacted this peg, they've stuck together and moved down as one. So the mass is effectively the 100 kilos of the hammer plus the 300 kilos of the post. So that'll be 400 V2. So let's process that. We'll be able to find the velocity at which this thing goes down. So if we divide both sides by 400, I'll have to use the method I've been using. Let's process that. And we find that the velocity is 2.214 meters per second. So now then, if we have the velocity before and the velocity afterwards, we should be able to calculate the kinetic energy loss. So let's do that now. Let's work out the kinetic energy of this thing when it's in its second state of moving down at this rate of 2.2. So kinetic energy is a half mv squared, which is going to equal to 1/2. The mass, in fact, is now 400 because it's this entire unit that's moving down together, times the velocity, which was 2.215 squared. We'll process that. Which is I make equal to 981 exactly, which is a good sign when I get a whole number. It's 981 joules. That's the second state. So theoretically, if we work out the original kinetic energy and take away this value here, then we should be in business. So the initial kinetic energy was half times 100 times the velocity squared, and it was travelling at 8.85 meters per second. And that was the initial velocity. If we take that away, the initial kinetic energy, take that away from the second kinetic energy, we should have a value. So let's process that. So 8.85 squared times 50 that becomes 3916 minus 981, which equals 2935.125 joules. That's the loss. And looking at our answer guide, they're getting 29.40. So yeah, we're within a sensible margin error. So just a quick review of what we actually did there. Worked out the initial velocity. Used conservation of momentum here to work out the loss in velocity because the thing slows down as it moves down together. Recalculate the kinetic energy. Take them away from each other and you've got the loss. Work that one through again. Do the entire question again as you need it. There is one additional part. It said the loss of and the overall work done. So the overall work done is going to be this 981 joules here. That's our kinetic energy, but we also need the potential energy of this unit here. So the overall work done, right, I'm going to make some of this smaller. There we go. Well, you could do that in your real exam. Okay, so what we're trying to achieve here, I'll do this in black now, is this is the kinetic energy, this thing here, of this situation. They're given us 80 millimeters for a reason. We can work out the potential energy converted here. So P equals mgh. The mass is 400 of it going down. Gravity is still 9.81. The distance travelled is 0.08. So we're going to end up with 400 times 9.81 times 0.08 equals 313.92. So the total energy in that system, the work done, as it were, would be 981 plus 313.92, which is going to equal 1295.17 joules, or 1.2, near enough 1.3 kilojoules. There we go. Do work through that second part of the question again, because that is a complicated one. Quite a lot going on, more than meets the eye. But a little trick is if you get in a situation where you've got a change in velocity, things are sticking together and moving on as one, that's a sure sign that it's conservation of momentum. Good luck with that one. It's a toughie.